space as well as complex leading space. So now we start with the inner product for general vector spaces. Alright, so let's see the vector space. Over C. So let's consider over the set of all complex numbers. Alright, so an inner product on V is a function. Okay. From the Cartesian product of V and itself to the set of all complex numbers, such that it has three properties. One is called non-negative property. So that so the inner product of a vector in V with itself will be non-negative. And this inner product is equal to 0. You can only x equals to 0 vector. The second conjugate symmetric. That xy, so the inner product of x with y is equal to the complex conjugate of the inner product y with x. So if we change the order of these two vectors, then we have to put the complex conjugate. So this is the second one. And the third one is about linearity. It's linear for the first argument. Alright, so that is alpha x plus alpha prime x prime and inner product y is equal to alpha x y plus alpha prime x prime. So you can see we have linearity for the first argument. Okay, so in any vector space V, if we can construct a function on a pair of vectors in V satisfying the following three properties, then this function is called an inner product on the vector space V. Okay, and so a vector space V over C together with an inner product on it is called an inner product vector space. That's sometimes we will omit the vector. Alright, let's take a couple of examples. We let CAB be the vector space of all complex valued continuous function on the finite interval from A to B. For example, f of t for example, polynomial functions okay, for examples, maybe, okay, for examples, or gt di 2 pi ft, okay, a phasor which is cosine 2 pi ft plus I sine 2 pi ft. So they are all complex valued continuous function on the finite cross interval from A. But they are not of set functions. Right? Now we define from the function as f g h b f of t and f of t are right, so we define for a pair of functions f and g. The function value is defined to be the integral from A to B, and the integrand is f of t times the complex conjugate of g of t. For all okay. Since f t times t bar is continuous, since the product f of t and g of t bar is continuous on AB, it is Riemann integral over AB i.e. the integral will be f of t, g of t, bar dt exists. And the final. Okay. So the integrand, this product is continuous, is a continuous function. So that over finite cosine AB is Riemann integrable. So it has a Riemann, and the integral exists and finite. And we know this is from calculus. So this is well defined. So this is well defined means that there is no ambiguity for the existence of this integral. And this integral is finite. Means that it's a complex number. Okay. Now we have to check such a function satisfies the previous three properties. First, we check Alright, so we'll check the previous three properties. First of all, for all f in this vector space, we know it's a vector space from chapter 35, right? We consider a function space like that. Or you may think like that the sum of two continuous functions is also continuous, right? In calculus. A scalar multiplication of a continuous function is also continuous. Right. So that so it's closed under vector addition and scalar multiplication. And it also satisfies all possible property. For example, the zero function serves as the additive zeros. And a continuous function multiplied with -1 give you its additive inverse. Okay. And with the addition, it's commutative, associative, and the 1 is the unit. So the scalar 1 multiplied with any function is the function itself. So we can check all the axioms for vector space are satisfied for this set. So it's, of course it's a vector space. But the important thing is we have to check the three properties here. Alright? So we check okay, now the integrand is non-negative. The integrand is non-negative. So that, of course, if the integrand is non-negative, then the integral must be non-negative. Alright? Now, if f is equal to 0, means that it's a zero function, then f 0, of course. So if f is identical to the zero function, then that the inner product of f with itself is 0. Okay. Now, if f is not equal to the 0 function, then there exists the P0 in AD such that f of P0 is not equal to 3. Okay? So if f is not the all 0 function, so we can find the point P0 in this first interval such that f of P0 not equal to 0. Okay? So we have to show that if we already showed if x is 0, then the interval is 0, but we have to show if the interval is 0, then f must be a 0 function. So we use the counterpositive property. Okay. Alright, so if f is not 0, we have to show that its inner product is not 0. So now by continuity, of f at t equal to t0, right? For all epsilon greater than 0, there exists a delta such that f of t minus f of t0 is less than epsilon. For all t minus t0 is less than delta. Okay? So, so here is the so suppose t, this is t0, okay? So T0 and FT0. So FT0 is not equal to 0, and we can find a neighborhood of T0. So this is a neighborhood of T0. Okay, so this is T0 minus delta, T0 plus delta. Okay, and so here is FT0 plus epsilon. This is FT0 minus epsilon. Okay. Alright, so by triangular inequality, we have that f of t, which is f of t minus f of t0 plus f of t0. Okay, and so the absolute value of f of t is this one, and would be greater than equal to f of t0 minus f of t minus f of t0. Right, and so this is f of t0 minus epsilon. Because the difference is less than epsilon, so that so this difference is a low bound. For all t in between t0 plus delta and the t0 minus delta. So for all, we have that. Okay. All right. So this is true. See here by continuity for any epsilon. Okay, for any, you can select any epsilon, then we can select which there exists a delta satisfying this inequality. And so we have that. Okay. So now, the inner product of f with itself is from AB FE squared. So this is greater than equal to that AB intersect with T0 minus delta, T0 plus delta, and the f of t squared. So we restrict ourselves to the interval such that this open interval. Okay, so this open interval intersect with AB. Okay, because that but this never empty. Okay. Most often, if T0 is in the interior point of AB, then of course that this is equal to this open interval, but open. But that's fine. Just so that and this is the low bound. So this is equal to would be equal to okay, it has a low bound here. So this is Ft0 minus epsilon square of dt. Right, and so the lower bound would be Ft0 minus epsilon square times delta. Okay? Because that there are three possibilities. AB is here, and we have T0 minus delta. This is T0. This is T0 plus delta. Okay. In this case, the integral would be this constant times 2 delta. But anyway, and this is low bound, or you may have AB. Okay, and This is T0, T0 minus delta, T0 plus delta. Or you may have AB T0, T0 minus delta, T0 plus delta. So you have three situations. Alright, and at least the length is, so the whole part is in here, and you have this one, you have this one. So the length is the low bound, which is delta. And the integral is constant. Alright, so you have that. Okay, so this is true. This is true for any epsilon and delta small enough. So by selecting epsilon less than this number, so we select epsilon, which is small, smaller than f of T0. Right, and so that the low bound is positive. We have okay, so starting from f not equal to, when f is equal to 0, the zero function, we know the this inner product is 0. Now, for f is not equal to 0, we prove that this inner product is positive. So we conclude that the inner product is 0 if and only f identical to the 0 function. Alright, so this is the first. Okay. So the harder part is here. Okay. To show that if f is not equal to 0, then the inner product of f with itself will be positive. Any questions? Okay, so if no question, then I will move forward to check the second part. Okay, so f of t, by definition, is f of t, g of t, 5. Okay, now we take so if we take the bar over the product, then we have to attack. And then we can move the bar out of the integral. So we will have the gt and ft. And so this is E and F. Okay? So we have the conjugate symmetric property. The third property, linearity, alpha f from alpha f plus alpha from f from and g. Alpha f of t plus alpha from f from t, t bar. Now by linearity of integral, integral has linearity, and so this is so now we have the linearity for the first argument. So, concluding, the function defined above is indeed an inner product on the vector space of all complex value continuous functions on AB. Questions? This is about the first example. Now I'll provide second example. So we let sub 1, sub 2, up to sub n be positive numbers. So they are all positive numbers. And we let W to be the diagonal n matrix. Okay? And the diagonal matrices are these n positive numbers. Now define. We define a function. Okay. W. Right. So we put the W as the subscript on the n-dimensional complex Euclidean space. Right, and goes to C as follows. X, Y, and W is defined to be Y, H, W, X. Right? So the means is that we take the Hermitian of Y. Remember, Hermitian of Y is the conjugate transpose. Okay? So what is this? That would be Y1 bar, Y2 bar, Y1 bar. And you have sub 1, sub 2, sub 1. And here you have x1, x2, up to x. Okay? And this is equal to sub 1, x1, y1 bar, plus sub 2, x2, y2 bar, plus sub n, xn. So the only difference from this function compared with the standard inner product for the Cn, because we can see the standard inner product for Cn, right? In there, the weighting, we put weighting for each term. For standard inner product, the weighting are all 1. 1, 1, 1, 1, 1, 1. So this becomes the identity matrix. Okay? But in general, we can put different weighting for different terms. Okay, and the weighting here is that 1, that 2, that n can be arbitrary positive numbers. Right. So you can look at this one, more convenient, or in a compact form. YH double. Now it is easy to verify that one. X double, which is sub 1 x1 sub 2 x2 square plus sub n xn square. And because sub i's are positive, and the square of absolute value are always non-negative, so we have to be sure the function value x interval with x itself will be non-negative. And equal to 0 if and only if this is 0, if and only if x1 they are all zeros. Because the weighting is positive, so that if this is 0, then every square term must be 0. So it will only x1, it will only, okay? So prove the first property. The second property. Okay, so we have H W X. Okay, so now so now if we put okay, we put a bar over all terms, then we have that, and so this is bar. Okay, so we have a conjugate symmetric property. Alright, from alpha from x from 1. So this is w. Okay. But the great property of metric multiplication. So this is okay. So prove the linearity for the first argument. So conclusion, this function is an inner product even. So you can see that we can construct infinitely many inner products on the set of all complex n-dimensional column vectors. And the standard inner product, just one of them. Okay, just one of them. So So that there are a lot of inner product we can have. Any questions on these two examples? So inner product space, from these two examples you can see inner product space, this concept is very general. It can provide us a very effective means or tools to study things like signal processing, or for example, if you consider Fourier analysis and want to do the Fourier expansion, then indeed you are considering an inner product on the set of functions which is finite energy. So okay, it is easy to see that inner product defined above is conjugate linear for the second argument. X beta y plus beta from okay, which is equal to beta y plus beta from x. So if you change order, so we from the conjugate symmetric property, and then by the linearity for the first argument. Okay, so we have this one. And this is beta bar yx bar plus beta from bar from and the beta bar, again by the conjugate symmetric property, we can exchange the order of x and y. So we see that if we want, for the second argument, the coefficient, when pull outside of the bracket, you have to put the conjugate bar over the beta and the beta. So that's called conjugate linearity for the second argument. Alright, now we define the node or length of a vector X in an inner product space. V as the square root of the inner product of X itself. So this is the definition of the length. And the line of thinking to put such a definition is from our previous experience on the n-dimensional Euclidean space, real Euclidean space, as well as the n-dimensional convex Euclidean space. And for norm, we have the following properties. 7.1.9 about the properties of the norm. First one, the norm, the length, always positive for all x not equal to 0. So if we have a non-zero vector, then its length is positive. Okay. Second, if you have a scalar multiple of a vector x, then the length will be the x value of the scalar times the length of it. Okay. Third one. Third one, we have choice inequality. So we have quotient. This is called quotient y. Inequality. Okay. So the absolute value of the inner product of x and y is an upper bound, which is the product of the length of these two vectors. That is called the Cauchy-Schwarz inequality. We also have triangular inequality. The sum of the length of the sum of two vectors in an inner product space is bounded by the sum of their lengths. So this is called the triangular inequality. Fifth one, if the inner product of two vectors x and y is 0, then we have Pythagorean equality. Then the square of the length of the sum of two vectors is equal to the sum of the square of their lengths. Okay. So this is called the Pythagorean equality. Right? So if and I think I can put them trigonometry. Okay? Trigonometry. Not just. Oh, I'm sorry. I'm sorry. I have to make a remark. So this is always true. If x and y is equal to 0, then we have the Pythagorean equality. Right? So in this case, i.e. Equal to 0, we call that x and y are mutually orthogonal. denoted as x plus y. So if x and y are orthogonal to each other, then we have Pythagorean equality, but the reverse may not be true for the complex case. So I make a remark here. In the real case, we have when only but in the complex case, Pythagorean equality does not imply orthogonality. The so-called real case means that all the inner product we defined when we consider over the real number, then all the conjugates can be removed. Okay, because conjugates only valid for complex case. For real case, we don't have conjugates. Okay, so in the real case, orthogonality is the same idea as Pythagorean equation. That is true because when we study the Euclidean geometry, we are considering the real case. So the concept of orthogonality is the same, is equivalent to the concept of Pythagorean theorem. Okay. So we have economically, but for the complex case, orthogonality is much stronger than the Pythagorean theorem. Okay, so it is possible that to have two vectors, the two vectors not orthogonal to each other, but satisfy the Pythagorean equality. It is possible. Okay, so that is a warning. Any questions? Okay, so before I give a proof, we will take a rest for 5 minutes. Okay, so we now give a proof of the properties of the norm. Right, so the first term. So we take the square of the norm of x. By definition, this is the inner product of x itself. So this is greater than 0 for all x not equal to 0 vector. Okay? So that is from the property, the non-negative. non-negative property of inner product. So this is implies that the square root of this is equal to 0. Right, so that is the first property. The second property, okay, alpha x by definition, alpha x, okay, the square root of alpha x, inner product is alpha x, and by the linearity for the first argument, and by the conjugate linearity for the second argument, we have that. Okay. Is that okay? Okay, and so now we have the square of the absolute value of alpha, and this one is the square of the norm of x. Now, by taking the square root, so we have, and this is the second part, right? Okay. Third one, we let R to be a real number. And we select alpha, a complex number alpha, such that alpha yx equal to the, because in general that we can all, this one is always positive, right? Absolute value. And so we can always find a common number, multiply with this number equal to this. And this is always possible. And so this is the phasor. Do you need me to elaborate this point? Okay. Let me take an example. For example, inner product is a common number. So any common number can be put in its magnitude, multiplied with a phasor, right? You know that, right? Any common number. Okay. Do you have any question about this? A common number, say 3 plus I4. Okay. So what is this? What is the magnitude? In the complex set, so this is alright, so 3 plus 4 is 3 here, is 4. So we have 3 plus 4. Okay. And then here. And we have the angle. length is 5 because by Pythagorean triangle, right? And the theta. So 3 is equal to 5 cosine theta. 4 is equal to 5 sine theta. So you know what is theta, right? It's called the polar representation, right? This is the polar representation of complex number. I think I asked you to, it's in the appendix B, right, of the textbook. So any complex number, this inner product is a complex number. And so a complex number can be represented by polar representation. This one is absolute value of the complex number. And multiplied with the phasor. Okay, because EI theta is cosine theta plus I sine theta. Okay? So now, y, what is yx? This will become to e minus I theta. Okay? Is that right? And so when you multiply with ei theta, this is becomes to. So what is alpha? Alpha is just this phasor. So the magnitude of alpha is equal to 1 because any phasor is magnitude equal to 1. Is that okay? So you understand why we can select alpha, okay, such that alpha times this inner product is equal to the absolute value of x from here. Any question? Yeah. Don't hesitate to ask me questions. Okay? If you don't ask questions, I barely believe that you have no question about my presentation. Okay, so alpha has this property, all right? So we can select alpha. Now, if not equal to 0, then this is repeat. Yeah. So from there, so if this then alpha is equal to so that you can move here. And the absolute value of alpha is equal to okay, I think that is enough. Now, from the non-negativity property, right? So we can consider this interval. Alpha is arbitrary real number here. And the alpha has been selected, okay, from here. Of course, if the interval is 0, the alpha can be chosen to be any phasor. Okay, but anyway, so we consider this. Okay, and so now by the conjugate symmetry property, we have minus plus okay. So we have 4 terms. Okay, remember, R is real number, so the complex conjugate of R is equal to R itself. Okay, so we have this 4. Now, by our selection here, this is equal to the X value of, okay, and this one is also equal to the bar of alpha, alright? Because we put a bar here, and if we change the order of x and y, then we get it here. And what is that? This is actually equal to x1 capital value for the set. So we have the same capital value of the inner product of x and y. Okay, so now we have x square, because this is the square of the norm, minus 2r, that's value of x, y, for that, because they are the same. And plus r square plus here, like that. Because alpha is the phasor. Alright, so now we let R to be 1 square if y not equal to 0. Let me see here. So if y not equal to 0, we let R to be square, and then we have square minus 2 square and the y square. Plus square and the square here. So So if we plug in back r into here, so we have this term and cancel one of them. Okay, so we have that. So that this is equal to x squared minus y squared xy squared. Okay, and then you move this term to the different side. So we have less than equal to square and by taking the square root, so we have the Cauchy-Schwarz inequality. Okay, so this is one way to prove the Cauchy-Schwarz inequality. There are other ways to show the Cauchy-Schwarz inequality. And I give you one which is more interesting. That indeed, by taking some degree of freedom, for example, r can be any arbitrary real numbers, and put some specific selected constant alpha, you can manipulate such kind of inequality. This is a very basic thing, okay? Because we use only the non-negativity property of integral as well as the conjugate symmetric properties. And these two properties are two basic properties of the inner product. And sometimes we will use linearity for the first argument if necessary. But the first two is very important. Non-negative property and conjugate symmetric property. These two are fundamental properties for any inner product. Okay, and so that would be a good formulation for us to prove inequality such as the Cauchy-Schwarz inequality. So we have. How about the triangular inequality? Once we have Cauchy-Schwarz inequality, then the triangular inequality becomes pretty easy. So let's see. Okay. Right. So by definition, the square of the norm is the inner product of x plus y is itself. And then we apply the linearity on the first argument and the conjugate linearity for the second argument. Unfortunately, the coefficients are real numbers because they are all ones. So we have x okay, so this is by linearity. Right now, but we take care of the middle two terms. But x y plus y x is equal to x y plus 4 x y. Right. So a complex number, either its complex conjugate, we will cancel the imaginary part, right? So that we have two of the real part of xy. Okay? 2 times the real part of this complex number. And the real part is an upper bar, which is just the s value. Okay? Just like here. The real part here. The real part always the length of the real part, the length of this segment, the leg are always less than the length of the hypotenuse. Okay, so the hypotenuse, because it's from the Pythagorean theorem. Anyway, so we have that. So the real part is upper bounded by the absolute value of the complex number itself. Okay, so we know the middle two terms has an upper bound. Do you need me to explain this? Or you just know it? If you need, raise your hand. Otherwise, I will move forward. Okay. All right. No problem. So let x equal to x plus I1. All right. So this is an arbitrary complex number, right? And so the absolute value of these, okay, is the square root of the real part of the square of the real part and add with the square of y. So the sum of their squares. And this is it's a low bound because y squared always is not negative. So this is low bound. All right, and this is that's the real x. So that is the real part. So this one that's the value, right? And always because the real part may be negative. So the absolute value always greater than or equal to x. And this is the real part. Okay. So you can see that the magnitude of v is a low bound which is equal to the real part of v. Okay. Right. So this is the magnitude of this is the complex number. All right. So finally, x plus y square will be less than or equal to x square system plus 2xy plus y square. Okay? So this is the square of the norm of y. And this is the square of the norm of x. And the middle two has an upper bound like this one. This is the first one. The second one, we will apply the Cauchy-Schwarz equality. So this one is an upper bound, which is the product of the lengths of x and y by Cauchy-Schwarz inequality. Alright, so here we apply the Cauchy-Schwarz inequality. And now we have a perfect square. Okay? We have a perfect square. So the square of the length of the sum is less than or equal to the square of the sum of their lengths. So by taking the square root, so we have less than or equal to x plus y. Okay? So we prove the triangular inequality. The fifth item. So if x and y are orthogonal, then again by expansion. Again, by expansion. Because they are orthogonal, so the middle two terms are zeros. Okay, they are zeros. So we have immediately or you can say so this is okay, so we're done. Okay, so we proved the properties, 5 properties of known. Any questions? Alright, so we move on. A set of vectors in an inner product space over C is called orthogonal if any two vectors inside if any two vectors in S are mutually orthogonal, i.e. V U for all V U in S. Maybe I put distinct. So a set of vectors is called an orthogonal set if you take two distinct vectors in X, they are mutually orthogonal. There is one special case. The zero vector is orthogonal. Is orthogonal to any other vector. Thing. Since 0, x is 0, x 0, 0, okay? Or you can decorate it. Okay, you can say 0 times x, okay? And the binarity, the conjugate linearity. So this is 0. So be careful. The zero vector always orthogonal to any other vectors by definition, because our definition is just that if two vectors has inner product equal to 0, then we say these two vectors are orthogonal to each other. Okay? So when we state so let X be an orthogonal set of non-zero vectors in an inner product space. Over C. So it's important. We are considering a orthogonal set of non-zero vectors. Means that this orthogonal set does not contain any zero vector. Then the X is linearly dependent. Alright, so if you consider an orthogonal set which contains a zero vector, then it cannot be linearly independent, because any set containing the zero vector will be linearly dependent. Okay, so that is very important to put the non-zero there. Okay. The proof here. Now we consider a linear relation. Okay, so we consider a linear relation on S. So alpha 1, V1 plus alpha 2, V2 plus plus alpha n, Vn equals to the 0. Alright, so that's such. So this identity is a linear relation. Okay? Remember, X can be finite set or infinite set. The X can have infinitely many vectors there. Okay? It is possible because our vector space may be infinite dimensional. So that so we may have infinitely many orthogonal elements in this orthogonal set. But when we say a linear relation, we always pick up a finite many vectors in X. For alpha 1, alpha n in C, and V1, Vn in S. Okay? So now we consider such an arbitrary linear relation. To show that X to be linearly independent, we have to show for any such linear relation, the coefficient must be 0. Okay? Must be 0. Okay, now, so take inner product with 3i on both sides. We have alpha 1 V1 plus theta plus alpha n Vn with Vi. Okay, so that is D0 and Vi. Okay, 0 Vi. Alright, so that it becomes to linearity of for the first argument. So we have alpha 1, V1, Vi, plus theta plus alpha I, Vi, plus theta plus alpha n, Vn, Vi, equal to 0, because zero vector interfere with Vi is 0. Okay? Because zero vector always orthogonal to any vector, so this is 0. But because they are orthogonal, so this is 0, this is 0. So this implies alpha I, big I equal to 0. But think with J, big I is 0 for all J not equal to I because they are orthogonal. Right? So all the other inner products are 0. So there's only one term left. But this implies that alpha equal to 0 since Vi is greater than 0. Why? Because we are considering non-zero vectors. So for non-zero vectors, this inner product always positive. So that alpha I is 0. Okay? So this is true for all I. Okay. So that X is linearly independent. Okay? So complete proof. Right. So this shows that any linear relation is trivial because of all coefficients are 0. Any questions? So orthogonality is stronger than linear independence. Okay, so it's stronger. But we are considering an orthogonal set of non-zero vectors. Okay. Always remember that. Okay, so now we have some simple theorem to state. In Rn or Cn, there does not exist an orthogonal set of n plus 1 non-zero vectors. Okay, so in n-dimensional real Green space, our complete Green space, it's impossible to have an orthogonal set of n plus 1 non-zero vectors. Why? Because if we have an orthogonal set of n plus 1 non-zero vectors, then we will have a linearly independent set of size greater than n. That is impossible because the dimension of either Rn or Cn is n. Okay, so that we have such a simple conclusion. Another theorem is that any orthogonal set of n non-zero vectors in Rn or Cn is the basis for Rn or Cn. Okay, and such a basis will be all orthogonal basis for Rn or Cn. Alright, so if a basis which is also an orthogonal set, then this basis will be called an orthogonal basis. Alright, so the proof, maybe I will say in simple consequence. 0. Understand? A simple consequence of 0, 7.1.2. Now we'll give another definition of vector x in the inverse vector. A vector x in an inner product space is called normalized. If its length is equal to 1, okay? A set is called an orthonormal set. If it is an orthogonal set of normalized vectors. Okay, so if an orthogonal set consistent of normalized vectors, so that every vector is not equal to 1, then such a set would be called as a normal set. So it's a combination of orthogonal and normal. So it's called also normal set. Any questions about this definition? Okay. So if no questions, then I will introduce a very important concept in inner product called orthogonal projection. Right, so the orthogonal projection of a vector x in an inner product space V onto a non-zero vector y in V is defined as a projection. Right? So y is in the subscript to denote that it's onto this vector. It's going to be okay, so the idea is here. So this is y vector in our vector space, inner product space V. And we have x here, x vector. And the projection, the orthogonal projection is that so that here, this part is the projection of x onto y. so that the difference, this difference, right? So this is difference, right? So this difference is orthogonal to 1. This is called a orthogonal projection. So okay? You get the idea? So we project the vector onto y, onto y. So this projection will be here, all right? So the red vector. And then the red is the difference. So this is the difference, x minus the projection. It should be orthogonal to y. So that's called orthogonal projection. You have many projections, right? In this way or in that way. But this is the so-called orthogonal projection. Okay? And the definition is here. It's this one. So we have to check. We have to check it. This is really satisfying this property. Okay? So I will put here a theorem 71115 x minus the projection x. Okay? It's orthogonal to the projection. Or you can say that the difference vector is orthogonal to this projection. That's the same. Because the projection is proportional to 1, so they are in the same direction or opposite direction. Anyway, we have this property. Okay, so we have to prove that. Okay, so now, by definition, the projection is x, y, y, y. Okay? Here. So, by linearity, we have minus okay, just by linearity for the first argument. And by the counter-linearity, so we have Morris conjugate. Okay, so we have that. So we have, and this is active, so that the bar, the effect of the bar is the same as no bar. Okay. And here we have the right. Okay. Here, so we cancel this one. Okay, so we cancel them, and you can see that these two terms are equal. So this is equal to 0. We have time. So we check that this is indeed true. So this is indeed satisfy our concept that this is indeed an orthogonal projection. Okay. Okay, and now we make a remark. If y, if the vector y is normalized, i.e. the length of y is equal to 1, then the projection of x onto y is equal to the inner product of x and y multiplied by 1. Because the denominator is equal to 1. So we don't need to write it out. Okay. Right. Right, and so I will stop here, and we will generate the projection, because this projection is just for a vector to project onto a non-zero vector 1. But we will extend the idea for a vector to project onto a subspace of an inner product space. And that will become more useful. Any questions? Okay, so if no questions, then I'll stop here.